Okay, let's go over problem number 61. Particle travels in a circle, the radius 10 meters at a constant speed of 20 meters per second. What is the magnitude of the acceleration? First step is always to draw the problem. So, okay, here we go. We got that's the path it's taking, and maybe the right here is the particle, and it's traveling in a circle. The radius right here is about 10 meters, and it's going at a constant speed, so we'll draw like a little arrow here and say 20 meters a second. 20 meters a second. What's the magnitude of the acceleration? So that's what we're looking for. So acceleration, what is it? All right. One thing we know here is that we're going to be doing uniform circular motion. So if something's undergoing uniform circular motion, we know a couple things. First off, we know that acceleration, which now we're going to call centripetal acceleration, is equal to the tangential velocity. I'll put a little t here to represent tangential velocity, squared divided by the radius of the circular path. And we know the radius, so that's great. We got that. And by this constant speed here, since they give it in meters per second, we know it's not an angular velocity, but instead the tangential velocity, the magnitude of the tangential velocity. So in other words, if you were to make velocity a speed by not having a direction, what would the value of it be? And here it would be 20. So we have 20 meters a second, 10 meter radius. So we have the velocity, we have the radius, we have everything we need. So just plug it in. We got the centripetal acceleration equals 20 meters a second squared, all divided by the radius, which is 10 meters. And what we're going to do is, yes, we can do the division. We're going to get 2 with the numbers, but let's check the units. So we get meters squared over second squared, all being divided by meters. This is going to cancel one of the powers of meters, and what we're going to get is 2 meters per second squared. And double check, meters per second squared, is that a unit of acceleration? It absolutely is. So this right here would be our answer. And seeing as they only gave us 1 sig fig in this problem, yes, you'd only have 1 sig fig. Moving on to problem 63. So a fairground ride spins its occupants inside a flying saucer-shaped container. If the horizontal circular path the rider follows has an 8-meter radius, at how many revolutions per minute are the rider subjected to a centripetal acceleration equal to that of gravity? Let's unpack that first off. So we get a radius. So right now we can say, okay, there's a radius, and it's equal to 8.00 meters. And great, they're giving us sig figs, in fact. And at how many, so it's saying at how many, so it's posing a question, revolutions per minute. So what we're looking for is revolutions per minute. Are the rider subjected to a centripetal acceleration equal to that of gravity? So that means that the centripetal acceleration equals gravitational acceleration, or the value 9.8 meters per second squared. So we're looking for when centripetal acceleration equals 9.8 meters per second squared. And what we're looking for is omega, or the angular velocity, expressed in, specifically we're expressing it in revolutions per minute. So we're going to try to find revolutions per minute using some of this other stuff. And that's what we're looking for. So a couple of equations we can write down. So first off, we have this equation: centripetal acceleration equals velocity squared over the radius. And then we have another version of this one, actually, where the instead of velocity, we're going to use angular velocity. So we have r omega squared. And where that came from is the fact that, so this is another equation, is the fact that the velocity, tangential velocity, equals the radius times the angular velocity. And we know that because of the units will work out. Radius is meters times Angular velocity is radians per second, but we can also just kind of ignore the radians. So it's just like 1 over seconds. So meters times 1 over seconds equals meters per second. So yes, this equation does check out. All right, so we're looking for angular velocity, but we're given information, this 9.8 meters per second squared, in terms of the centripetal acceleration. And we're given the radius, so it looks like actually all we're solving for is the angular velocity. So we can just rearrange this equation for angular velocity. So for that, angular velocity is going to equal the square root of the centripetal acceleration divided by the radius. Plugging these values in, you get the square root of 9.8 meters per second squared, all divided by 8.00 meters. And what's going to happen is the meters are going to cancel, and we get 1 over second squared, but this is under a square root, so we're going to get whatever the answer is going to be 1 over seconds, actually. And that is exactly what we expect. We expect 1 over seconds because this angular velocity is essentially radians per second. But remember, radians aren't really a unit here. So we're kind of ignoring the radian. So it's like 1 over seconds. But that is not our final answer. So whatever our final answer on this step is, so let's just say this was 5, it's not. But whatever that answer was there, what we're going to do is we're going to try to convert this from 1 over seconds, and we're going to try to convert this into revolutions per minute. We're going to use some dimensional analysis. So first off, let's put the rads back in, radians. And so let's go to revolutions. And we need to figure out, okay, for every 1 revolution, how many radians is it to get to 1 revolution? Well, it's 2 pi. 2 pi radians for every 1 revolution. All right, that will cancel the radians, and it will give us revolutions. And so we got revolutions per second, but of course we want revolutions per minute. So what we're going to do is have 60 seconds up top and 1 minute on the bottom. That's going to cancel the seconds. This is just dimensional analysis you learned in chemistry. And then we get revolutions per minute. So take this number, whatever it was, it's not actually 5, but it is this value. You're going to take this value, this omega, put it right there, divide it by 2 pi, multiply it by 60, and then you'll get your final answer, which will be rounded to 1, 2, 3 significant figures. All right, next problem is number 65. So the first part is a 22 kilogram child is riding a playground merry-go-round that is rotating at 40 revolutions per minute. Let's just stop right now and put in here that we're rotating at. So omega is equal to 40 revolutions per minute. So we recognize that this is omega. What is the centripetal force exerted if he is 1.25 meters from its center? So the force, centripetal force, is what we're looking for. That's what we're solving for. And we have a radius of 1.25. So that's some of the basic information they give us. Now, we can draw this. So let's draw a circle. We got this kid, which is going to be represented with just a dot. And it is a radius away from the center. And this is going around. So it has an angular velocity going around here. That's omega. And this child is feeling a force pulling them inwards. And the reason that there's a force pulling this child towards the center is because if there wasn't a force pulling him towards the center, this child would just go in a straight line. All objects go in a straight line unless there's a force acting on it. So there must be some kind of force acting on it to turn because there's an acceleration. Newton's first law. If there's acceleration, there must be a net force. So the net force is towards the center, and it's going to be our centripetal force. So let's just write down Newton's second law first off. Sum of all forces, it's always a good place to start, equals mass times acceleration. In this case, the sum of all forces is the net force. That's always the case. Sum of all forces is going to equal the net force. In this case, the sum of all forces is going to equal the centripetal force, because that's the net force. The centripetal force is always just going to be the net force when it is undergoing uniform circular motion. Uniform circular motion is just a special case of this generic Newton's second law. The centripetal force is going to equal the mass times the centripetal acceleration. So it's just a rebranding of this one for this case. Let's see what we can go from there. So we have the centripetal acceleration. We have a formula for that. We have, in fact, two formulas for that. We have velocity squared, that's tangential velocity. So in a straight line velocity over squared over the radius. And it also equals the radius times omega, which is the angular velocity squared. So which version of the angular acceleration you use depends on what you have or what you want to look for. We have an angular velocity, so we're probably going to stick with this version of the angular acceleration. Let's plug that in. So we got force, centripetal force equals mass times the radius times omega squared. Let's just double check we have everything. We were given the mass, we were given the radius, and we were given the angular velocity. However, we weren't given the angular velocity in the correct units. They need to be in the correct units. So we're just going to go ahead and fix that really quickly. So what we have is 40 revolutions per minute, RPMs. We don't want RPMs. We want radians per second, or just per second, 1/seconds. So what we're going to do is we're going to multiply by a fraction that is going to get rid of the revolutions. So we're going to have revolutions on the bottom, and we're going to put in radians. So we need to have something that compares radians to revolutions. There are 2 pi radians for every 1 revolution. That's going to cancel the revolutions, and it's going to get us radians. So now we have radians per minute. Let's multiply by 1 minute is 60 seconds. That's going to cancel the minutes, and it's going to get a second, so our ending unit is going to be radians per second. So what we need to do is take 40, multiply by 2 pi, divide by 60, and that is going to get us our angular velocity, but in the correct units. Bringing in a calculator, what we can see is we have 40, and then we're going to multiply by 2 times pi, and then divide by 60. So that's going to get us 4.188. This is an intermediate calculation, so let's just keep some of the extra sig figs. So 4.188. Everything here has been reporting in 3 sig figs, so we're probably going to round our answer in the end to 3 sig figs. And that is, of course, radians per second. All right, continuing, now let's piece this all together. We have the centripetal force equals the mass, which is 22.0 kilograms, and then we're going to multiply by the radius, which is 1.25, and then we're going to meters, and then we're going to multiply by the angular velocity that we just found, 4.188 radians per second squared. So all of that squared. And the units, let's just check the units really quickly first. So we're going to get kilograms times a meter times radians squared. But again, radians we can kind of ignore, so forget about the radians. And we get over seconds squared. That should look familiar. That is a Newton. So we got the units correct. The units are definitely going to give us a force. So now let's just plug in all the values. 22. So we get 22. Let's clear this. 22 times 1.25 times, and we'll just do 4.188 times 4.188 because that's what squared means. So that is 482, and now we'll round to 3 sig figs, so 482. So I'm getting 482 kilograms times meters divided by seconds squared, or in other words, 482 newtons as the answer to part A. So that is part A. So for part B, all we're doing is the exact same problem, essentially, except instead what we're doing is we're decreasing the angular velocity. So angular velocity is going to go down to 3 revolutions per minute, and increasing the radius, so increasing how far away this child is from the center of this merry-go-round. Right now, we can kind of make some predictions of what's going to happen with the force. Looking at this equation, we have the radius and we have angular velocity squared. So angular velocity is being squared, which means any change that happens with angular velocity is going to be magnified much more. It's going down by a large amount and is being squared. That is going to magnitude the difference. So this is really it's like getting extra double down. And the force, the radius is going up though. So one factor is going up, but then we have another factor that's going down and going down a lot because it's squared. So it has almost twice the impact. So I predict that the force is probably going to go down. I actually haven't solved this before, so we'll see what happens. Let's just plug in our values. So instead of 40 revolutions per minute, we instead have 3 revolutions per minute. So we can do the same math of 3 revolutions per minute. Here we go, we got the calculator back out. So we're going to do 3 revolutions, multiply by 2 times pi, and then divide by 60. That's going to get us about 0.314, so essentially pi, but just move the digit 1. So 0.314, I think, or 14. Whoops, that was a 5. There we go, 41. We can keep that many digits. So this equals the math. Math is staying the same, 22. I'm going to drop the units for now because we know what units it should work out. It's because it's the same equation. The radius got changed. It is now 8 meters. So we're multiplying this 22 by 8. And then we're going to multiply by the angular velocity we just found, squared. 0.3141, and square that. Let's break out the calculator again. We got 22 times 8 multiply by 0.3141 times 0.341141. All right, and we get 17.3. So 17.4 when we round up, and this is going to be newtons. So in part B, we have a smaller centripetal force, which is, like I said, what I expected, because the angular velocity went down so much more than the radius went up.